Okay, so we're back. So we're gonna do inertial to not inertial Jacobi to inertial transformations today, and maybe the other transformations. Yes, I'm just gonna clear my terminal. Okay. So now let's open transformations. Alright, so all of these are done. Time to do some research. Okay, are you here? Jacobi. Jacobi. In later sections, we will consider the planar, circular, restricted three-body problem as one of our main models. We derive it by first considering the general planar three-body problem using Jacobi coordinates 191, 219. The center of mass rho equals 0 in accordance with 1.5. I don't know what 1.5 is. It's somewhere down there apparently. Where P equals K equals 1 to 3 mx kx over m over total m equals n1 plus m2 plus m3. Okay, so this is a normal setup. The transformation of 1.11 is the yeah, this is some deep math, which I do know if I'm actually willing to read this thing, but I'm not willing to read this right now. This is fun. Two-body problem. Yes, this is okay. Never mind. How to convert between Jacobi and inertial coordinates. X. So I'm going to assume this is related to this is all just X. These are all generic. It could be position, velocity, or acceleration. So yeah. Okay. Total mass. Do we use total mass real quick? Yeah, I'll do total mass. Void Jacobi to inertial acceleration. Tab, complete this whole thing. Thank you. Quantity and thrust equals particles dot n. Okay. Now this is the part. This is kind of going to be the part where I can actually do logic. Xi, so force size Ti equals. Okay, so current comeback. Let's just use this logic. How do I reverse that whole thing? Force size Ti equals 1. I is less than. And I'm only going to deal with the normal particles for now, and then I'll deal with test particles. So the plus I, and now what? There's gonna have to have some loop counter, so. Double current total mass. Okay, so it seems that the relative coordinates, so the zeroth coordinate's the center of mass, so if I do vector com equals, I think I have a particles.com. No, I don't. It's like that simulation. It's in the simulation class, and I'm not gonna bother making a simulation wrap in a simulation. That simulation should not be touching this internal core. So, guess I have to implement that myself. How am I supposed to know XJ? If I want XJ, do I want to just have some relative coordinates? Orvix, have you produced? Oh, you're the WHFast article. Okay, let's check that out. Jacobi. Okay, so 2, 3, 4, 5, 6. So the Jacobi coordinate Ri of the ith particle is the position relative Ri1, the center of mass of all the particles interior to the ith particle. Ri equals Ri minus 1, where Ri is the center of mass of the previous, and Mi is the sum of the previous. That's what I'm getting. Previous and current. Hamiltonian, yeah, I might eventually need this WHFast article later, but I'm just doing transformation, right? I only care about the Jacobi part. Okay, I don't care about the actual WHFast code for now. Jacobi coordinate transformations. I had before primes in the Jacobi coordinates. We thoroughly tested the conversions to and from Jacobi coordinates to ensure they are unbiased. This task turns out to be much harder than we naively expected. As an example, consider the following algorithm, which is formally equivalent to the above but numerically much less stable. R0. For I to n-1 do. What is this? This is a weird form of pseudocode that simultaneously looks like math. and Python. This sounds weird. This looks weird. But okay, let's examine this. Okay, this is the Cartesian to Jacobi. Okay, so I have to calculate the total mass for the whole thing. Okay. I don't think this part doesn't matter if I use backwards or forwards iterations. I'll just use my trusty method. I is less than not n. Yeah, it's n. Plus I. And we just n minus 1, so I think m0 is the first, so we have 2. Sometimes it's m1 as first, sometimes it's m0 as first, and it's confusing me in math articles. Let me just continue on. Double m equals 0. For size t, it's just m plus equals particles dot mu's index it could be PJ. Do we trust PJ or particles more? You know what? If they are both wrong, who cares? Yeah, I'm just gonna do this. Particle.mu's index I. Alright, so now that we have this guy. So now I have our summing loop here. When you know and do that, I'm just gonna pragma this thing. Pragma won't be parallel 4. For size t I equals n minus 1. And now we have I minus minus is greater than 0. So now we have this loop done. It's 1. Okay, so not down to 0, to 1. Which means I could reduce this thing. But let's do 1. Let's put that in there. I is greater than 1 minus I. Okay. That's better looking. I do not care about the weird naming. Also, I thought I made it all caps constants. Alright, opening this now gives me yes, okay. R now equals R minus mi times R prime I divided by mi. Okay. Vec3 R equals particles on mu's index 0 times m. Wait, no, wrong place. Particles dot mu's index 0 times m. And I think this arrow notation is basically assignment. So I'm gonna treat it as such. R equals R minus, ignoring that, R minus, no, the R is in the brackets. Mi, so that would be mu's index I. Probably could use PJ instead here, but that'll be shorter, but let's use that anyway. And here it should be PJ. Times Ri, so that would be that. You then divide by mi. Okay. M. So now we actually have to, now we're gonna read particles. Particles dot positions index I equals PJ dot particles index I plus R. Accelerations index I plus R. And then you multiply equals R by mi minus 1, which can be easily done by doing m minus equals PJ dot mu's index I. And then R times equals M. And at the end of this, it's R over M0. Particles dot equals R divided by PJW's index 0. Okay. Surely this is correct. I've literally followed the exact same code, that pseudocode that the article gave. And it's a reputable source. Claude, hopefully you won't decide that this is wrong for some reason. Is this correct? Don't give a fix, but tell what the error is. I mean, yeah, that's pretty trivial. But wait, when there minus here, am I supposed to trust Claude? I'm just gonna move you here. Should I give it, yeah, let's just give it the exact same. This is the pseudocode in the paper I was following. Let's check near the beginning and to see what the notation here is. Excluding the first particle, I'm just gonna make sure. I'm just gonna send the exact copy here. Should I just copy this whole thing? Let's do that. I'm not gonna ask it. So, is this code correct? I'm not sure if I should be trusting Claude Haiku or the paper. I mean, Claude has a low hallucination rate, but do I still trust Claude Haiku with this? Yeah, I mean, this is some basic math, not like some complicated integrator, so I guess it's fine to trust Claude over that. It might be some typo. I mean, a pretty binary thing to notice. Alright, now is this done? I'm gonna send this. Send it. Oh yeah, and I'm just copy this whole thing. Well, first I'm just gonna fix the formatting on here, which is that's how the autocompleter in my formatter did that. That's gonna get auto format by clicking format out of that. I'm just gonna fix that like right now. Void Jacobi to initial P. Positions. And positions. and positions. Now this looks correct. See, I'm an actually competent programmer. I don't need Claude to tell me what to write. I only need the Claude to tell me if it's correct. This whole thing. PV. I'm also just gonna change it to R pause and R vel. Velocity is index 0 times m. R pause. R pause. R pause. R vel times equals m. R vel equals R plus pjs dot muse index I times R pause R vel times pj dot velocities index I all divided by m. Equals pj dot velocities index I plus R vel. Oh yeah, I forgot I have to update this section too. Particles dot velocities index 0 equals R vel over pj dot muse index 0. Nice, so this is done now. What's it? Should I ignore the 10 billion words? Oh yeah, and thresh. I forgot about you. You here need to be used somehow. So now we have inertial A, so can we just put in the size Ti equals n thresh I is greater than n thresh minus I. Why did I put this in here? When I could just reduce the code, lines of code somewhat like that. plus equals and plus equals and plus equals. So size D now R. Particle acceleration. Yeah, that part's unnecessary. So I think the only thing that's gonna happen in the test particles section is the particles acceleration index I. The way to think about test particles is to just treat them with a mass of 0 in the math. For size C equals 0, I is greater than n slash minus I. What we do is very simple. Particle acceleration index I plus equals R. Yank this one line and dump it here. When indicates replace with positions. And here there's one more thing to do. I have to also update two things this time, position and velocity, so I can't use single statements, sadly. I equals n minus 1. Yeah, I forgot. This also has to be n thresh, not n. I is greater than n thresh. Minus I. Particles positions index I minus equals R pos. Particle velocities index I minus equals R vel. Okay, nice. Now I'm gonna commit this. Added Jacobi to inertial. And finally, just nasty build. Okay. How to run Clang format? I forgot what it is, bro. Oh, just Ninja Dusty. Let's check out what it did. C/transform.cpp. Wait, this thing has opinions on the reduction syntax? That's weird. Okay. I guess it wants that. I'll take it. So what does it want in the include? Q. I don't want it. Include. Okay, it looks like it just added a namespace or something. I don't know. Yeah, I think it was just adding a namespace comment. Git commit am formatted code and git push. Alright, I think I'll just end the video there for today.